A few years ago, I started teaching a statistical linear models course where my students get to explore all types of models on data. And every year for the final project, I'd give them a canned data set that I knew everything about because I wanted to test if they could tease out all the facts that I knew. Well, it was never really a really interesting project for them because the data set was not something that interests them. And it was something that I honestly knew too much about. So I wanted to create a richer experience for them. I ended up partnering with the library at Harvey Mudd because they had all of this wireless data and they had students coming in and out, but they couldn't find a relationship between wireless usage. They wanted to know, are students on their iPhones or their iPads or their smartphones, and how are they connecting to the wireless system? So I said, hey, give me this data and let me give it to my students. And maybe that can be their final project. Well, all of a sudden, my class became hooked. They were excited to do regressions on this data set because they could see the necessity of it. That's what I love about regression. Now, in regression, we look at the association between two or more quantitative values. And we're going to begin to look for whether one of the variables causes or predicts changes in the other variable. For example, things like homework scores and test scores, or even maybe the length of time that a baby spends in gestation, inside the mother's womb, relative to their birth weight. How are these two things related? Now, linear regression deals with some really interesting things. We're first going to start with a response variable, y. Now, this is our dependent variable. This is the target. This is what we might use to measure the outcome of our study or the outcome of our experiment. We also need some variables that's going to try to help us explain that response. And we call that the explanatory variable. That's x. X is our independent variable. You might also hear it called the predictor variable. We're going to use it to explain the changes in our response. And so now we're going from having two independent sets of observations to pairs. Each of our x1 is paired with a y1. x2 is paired with a y2, and so on. Now, in linear regression, we're looking for the association between two variables, and we want to know, could we represent this association by a line? Could we fit a line to that relationship? So in essence, what we're going to look for is the effect that one variable has on the other. Now, perhaps the best way to explain this is by example. Let's imagine ourselves as wheat farmers in Kansas. All right, for the past 10 years, at the end of the season, we've recorded the total amount of rainfall and the average height of our wheat. And we'd like to know, does rainfall have any effect on our wheat yield? All right, so we've got 10 data points, each of them that's recording the amount of rain, which is measured in inches, and wheat growth, which is measured in inches. Let's stick this data into R. I'm going to call it rainfall. So rainfall is going to use the C function to combine my data values for rainfall. And then wheat is likewise using the C function to combine my data values for wheat. And notice I'm going to do a summary statistic. So I want to pull out the summary statistics for that data set. And I'm just using cbind to combine them so that summary gives me both of those results. Now, our summary statistics show that rainfall ranges from a minimum of 3.07 to a maximum of 6.77 inches, with a mean of around 4.9. Notice here too, wheat ranges from 78 to 119 inches, and it has a mean of around 95.5. Now, let's have a look at our scatter plot. Notice here we see that the data suggests there might be a nice linear relationship between rainfall and wheat yield. We can summarize that relationship by fitting a regression line. So our regression line is a straight line that does a couple things for us. First, It's going to describe how our response variable, say y, changes as our explanatory variable x changes. What it also does is allows us to minimize the square difference. We call these the residuals. The difference between each observation and the fitted line. Now, the reason we minimize the square difference, as opposed to, say, the absolute difference, is because of this. When we're fitting a line to data, we get the best estimates of the slope and the y-intercept when we minimize the square differences. Now, here's what our linear regression model looks like. And remember, our parameters are unknown. These are population parameters. So we set y equal to beta naught plus beta 1 times x plus epsilon. Now, this beta naught is the y-intercept term, beta 1 is the slope, and epsilon is the error term. Now, notice the Greek letters here. Our model is about an underlying population. So in this case, epsilon stands for a series of random errors, right? Epsilon 1, epsilon 2, all the way out to epsilon n. And we assume that these follow a normal distribution. They've got a mean centered at 0 and some standard deviation sigma. So that's one of our model assumptions, normality of the residuals. Now, the standard deviation sigma, well, it doesn't vary for different values of x. And this is the second assumption, that we have constant variability in our data. Thirdly, those epsilons, they're associated with observations that are independent of each other. So each of our epsilon values have to be independent. So those are our assumptions for the regression model. And we're going to have to verify that our data meets those assumptions so we can fit it using a regression line. Now, the way that we get our slope and y-intercept, that beta naught and beta 1, is to estimate it from our data, right? This is our evidence. And so notice when we talk about estimates from our sample data, we're using these hats over the betas. So you'll see a beta 1 hat and a beta naught hat, which tell us that that's coming from the estimate from our sample. Now here's our linear regression line with the parameters that we've now estimated from our sample data. So y hat equals beta naught hat plus beta 1 hat times x. All right, here's how we're going to estimate that beta 1 hat. It's equal to the ratio of what we call the sum of squares of xy over the sum of squares of sx. Now we've seen this before. Look at that numerator. That's the sum as I goes from 1 to n of x sub I minus x bar times y sub I minus y bar. Now this might remind you of the numerator when we calculate the covariance between x and y. That's exactly what it is. So it's a measure of the variability between x and y. And now notice in the denominator, we're dividing by the sum of squares x. So the sum as I goes from 1 to n of xi minus x bar squared. This is a measure of the variability in x. So that's what we use to estimate beta 1. We're going to estimate beta naught really cleanly. So our beta naught hat is just equal to the mean of our data, y bar, minus our estimate for beta 1 hat, times the mean of our x values, x bar. Now, the way that we estimate our model parameters is through the method of least squares. So this is going to allow us to fit the line through the points that's going to minimize the sum of the vertical distances from the point to our regression line. Okay? So we're going to minimize y minus y hat quantity squared. Now, conveniently, R will fit a linear regression for us. And we just use the function LM, which stands for linear model. Now notice, after LM comes our response variable, in this case, wheat. And then it's followed by a tilde. Now the tilde tells R that what we want to model, wheat, on the explanatory variable that follows it. And in this case, that's rainfall. So wheat tilde rainfall means model our response variable y on our independent variable x. Now, it helps for us to store that linear model because we're going to do some further analysis on it. So here I just call that wheat.mod to let me know that this is my wheat model. And in fact, we can use the summary function on this wheat.mod and see our regression output as we see here. Now notice R gives us a ton of regression output. Let's walk through that together. The call, this tells us what our regression model is. So in this case, wheat is being regressed on rainfall. Notice too, we get the summary statistics for the residuals. So we can do a quick visual check to see if our residuals have any outliers. We can check and see if the median is close to 0, because remember, we want those residuals to be normally distributed. R also gives us the coefficients. So notice this is where we're going to find our estimates. So our beta naught hat, which is 45.0408, and then also our beta 1 hat, 10.1691. So here we find the estimates for our y-intercept term and our slope coefficient. Now, we'll go further into the rest of that output in later lectures. So for now, let's look at a plot of our wheat data with the estimated regression line. So this is the regression line that we fit to this data. Now you see how well our line seems to fit the data, right? And remember, this is because we chose the line that minimized the square differences between our data values and that estimated regression. All right, so question, how would we then write out the equation of our linear regression line? Right? So we can actually solve for this directly with our data. Let's do that for the slope parameter. So for beta 1, remember we said our beta 1 hat is equal to our sum of squares xy over our sum of squares x. So this is the sum as I goes from 1 to n of xi minus x bar times yi minus y bar, all over the sum as I goes from 1 to n of xi minus x bar quantity squared. And notice when we plug in our x and y values, we get 10.1691. And so this matches our result from R. All right, so now we've got this estimate for beta 1 hat. How are we going to solve for the y-intercept term, our beta naught hat? Now remember, this equation is y bar minus beta 1 hat times x bar. So we can plug that in as well, 95.5 minus 10.1691 times our x bar, 4.962. So that gives us 45.0408. Now we're ready to see our regression equation. All right, we're going to plug in our estimates for beta naught hat and beta 1 hat, and that is going to be our y hat. Here's what we get. Y hat is beta naught hat, 45.0408, plus beta 1 hat, 10.1691 times x. So we can use a regression line to predict the value of the response variable y for a specific value of the explanatory variable x. We call this value a predicted value or a fitted value. Now we have to be careful here about extrapolations, right? We can't conclude that our regression line is an accurate model outside of our sample data. In other words, just because our data supports a linear relationship between x and y, it doesn't mean that that relationship is going to hold when we get values outside of the range of x. And so in that case, predictions for y, for x that are sort of far away, they're often not that accurate. In fact, have you heard of the 7 deadly sins? Well, statisticians have the 3 deadly statistical sins. First, if you don't randomize, that'll get you every time. Second, accept the alternative. Again, we either reject the null or we fail to reject the null. We never accept the alternative. Third sin is extrapolate it. Just don't do it, right? Unless you are interpolating within the range of your data, you don't want to extrapolate outside of your data. Now, we can use our regression line to actually predict a value of wheat yield. Let's do that for 5 inches of rain. So let's say we wanted to predict what wheat might we expect if we had 5 inches of rain next year. So in this case, we're going to take our regression line, y hat, set it equal to our beta naught hat, 45.0408, plus beta 1 hat, 10.1691, times 5 inches of rain. Notice that this predicts that our wheat yield would be slightly over 95 inches. Now, what if we wanted to also predict it for, say, 100 inches of rain? Well, in this case, we go right back to our regression equation, but now we're plugging in 100 inches of rain instead of 5. Now, that's going to give us some pretty tall wheat, right? 1,061.95 inches. And in fact, if that prediction were true, we'd probably all be wheat farmers in Kansas right now. We're also going to need a way to understand how well our regression line fits the data, right? And so our residuals are going to be what we use to help us do just that. Let's define a residual. This is going to be the difference between our observed value, say y sub I, and the predicted value by the regression line, y sub I hat. Here we use E sub I to represent the residuals. So EI is equal to YI, observation, minus YI hat, predicted value. Now, many of my students get confused at this point because it seems like our residuals, this EI, is the same as our errors, that epsilon I. So let's clarify that. Now, our epsilons, they measure actually the deviation from the observed value, Y, to the unobservable true regression line. So this is the regression line with the parameters from our population. So YI minus beta naught plus beta 1 XI. So that's what our epsilons are. But now the residuals, on the other hand, they measure the difference between the observed value and the estimated regression line, YI hat. So YI minus beta naught hat plus beta 1 hat XI. Now here's a plot that shows what the residual is. So for a given observation, YI, the red dot, we can find the distance from that point to the regression line. And the value on that regression line is YI hat. This is the estimated fit for that value. The difference between those, Y sub I minus Y sub I hat, is what we call the residual. Now, in order to analyze our residuals, we need to plot them. And we're going to look at a residual plot. Now, this is just going to be a scatter plot of our residuals against our explanatory variable x. And the mean of the least squares residuals should always be equal to 0. So we're going to look for residuals that should be roughly centered around 0. Here's what good plots are going to look like. If you've got some great residuals, they look like complete randomness. Maybe there's no pattern. You should have approximately the same number of points below 0 as you have above 0. Whereas a bad plot, you're going to see some obvious patterns in your residuals. Maybe you've got funnel shaped, or maybe there's a parabola, or you might have more points above 0 than you have below it. Take a look at this example. Here's a good residual plot. You've got data values that are nicely centered at 0, and the points are well balanced. You've got approximately the same number of points that are above y equal to 0 as you have below y equal to 0. Now this next plot, is not so great. Notice how your residuals sort of fan out as your predictor variable x increases. So their variance is increasing as our fitted values increase. We actually have a name for this fanning out of the residuals. We call it heteroskedasticity. See if you can say that fast, just 3 times in a row. Heteroskedasticity, heteroskedasticity, heteroskedasticity. Now, of course, if the spread stays the same, the residuals are going to look the same everywhere, and that's called homoskedasticity. Now, the next plot you see is also not so great. There's another kind of pattern left in the residuals, and that means there's more structure that we need to account for in our model. So we would need to remove that and place it in our model and then recheck our residuals. Now here's a residual plot of our wheat data. There appears to be a pattern, but remember we've got so few data points. This probably isn't the best way to determine if we've got normality. But we can always go to your old favorite, the QQ plot. Now a look at our QQ plot confirms that our data, even though it's small, is satisfying that normality assumption. All right, so now that we fit a linear model to our data, we need to figure out how good is it, right? How well does it fit our data? Is the model strong enough that we could actually get good predictions from it? So let's introduce some terminology that's going to help us assess our model fit. The first is called the regression sum of squares, or SSR. The regression sum of squares measures the variation in our y hat. And so it's defined as follows. The SSR is equal to the sum, as I goes from 1 to n, of y sub I hat minus y bar quantity squared. So again, it's telling us how much does our regression line vary from our overall mean. Next is the error sum of squares, SSE. This measures the residual variation in y due to error, right? This is also just our sum of squared residuals. So it's the sum, as I goes from 1 to n, of y sub I minus yi hat quantity squared. Or you can just imagine it as your sum of ei squared. Lastly is the total sum of squares, SST. This measures the total variation in y. Right, so the sum, as I goes from 1 to n, of y sub I minus y bar quantity squared. And we could actually show that our total sum of squares is equal to the sum of squares due to our regression plus the sum of squares due to our error. Now, we use what we call the coefficient of determination. This is r squared. And this is going to give us a measure of what fraction of the variation in y can really be explained by this linear regression on x. Here's how we define r squared. It's equal to our sum of squared regression divided by the sum of squares total. Okay? You could also write that as 1 minus the sum of squares error over the sum of squares total. Now let's motivate that for a second. If you're looking at your sum of squares regression, if your regression model is a really good fit to your data, then your sum of squares regression is going to be big relative to the sum of squares total. So you're going to get a pretty high r squared value. But if your regression doesn't give you a lot of information, it's going to be lower. So your sum of squares regression will be lower, and more of your data, more of your information is going to be in the sum of squared errors. So you'd get a lower r squared value. So if we've got an r squared of 0, that tells us that y can't be predicted linearly from a model with x. All we have is sum of squares total and sum of squares due to error. The regression sum of squares isn't really accounting for any information. On the other hand, if we get an r squared value of 1, that means that y can be predicted from x without any error, right? All of our total sum of squares is encapsulated in the regression sum of squares. What's more interesting are r squared values between 0 and 1. So that tells us to what extent is y predictable by x. Right? So for example, we had an r squared value of say 0.1. This means that 10% of the variance in y is predicted from x. Or an r squared value of 0.8 tells us that 80% of the variance is predictable. All right, let's look at some examples of data with various levels of r squared. Now here you see an example of data that has an r squared of approximately 0.25. You see some association between the two variables, but that linear relationship really isn't that strong. Now the data in this next plot has an r squared value closer to 0.7. And notice it has a stronger linear relationship, and we can start to see where an increase in y can relate to an increase in x as well. Now this third plot has an r squared value of around 0.95. So 95% of the variability in y can be explained by this linear model with x. Now this shows a really strong linear relationship between x and y, and you can see how tightly those points are clustered. Now, we can't forget to check our model assumptions. Remember, we made a couple assumptions about especially our residuals. We assume normality, right? And so in order to check for normality, we'd actually look at a QQ plot of our residuals. Second, we have to check for constant variability. And again, this shows up in our residual plot. Now, in order to check for independence, that's a little bit harder. We really have to examine how our data values were collected to make sure our study doesn't involve any type of dependency between our data. So it's more difficult to pull that out of a graph. And then lastly, we check for linearity. And so just a scatter plot of our data will tell us whether or not we could fit a linear regression to it. Now, one thing to note, it's always important to check the assumptions of your regression model. You've got to check whether they've been met. Otherwise, your results really aren't going to be valid. And in fact, those are some of the most common pitfalls that my students fall into. Here's the first one. The first pitfall is that they fit a linear model to nonlinear data. Notice in this graph, the data is slightly curved, and while this linear regression fit isn't too bad, check out those residuals. Right, the residuals aren't normal, and we see that same curved pattern showing up in a similar pattern in the residuals. This is the same as what's in the original data. Second pitfall, fitting a linear model to data with a non-constant variance. All right, notice here, the variance of y is increasing as x increases. So this variance isn't staying the same. It's still heteroscedastic, our new word for this lecture. Here's a third pitfall, fitting what appears to be a good model, but actually has non-normal error. Now in this case, the initial scatter plot might actually fool us into fitting a linear regression. But look at your residuals. Now that should make one of your eyebrows raise up. I mean, the residuals, they aren't really centered at 0, and a QQ plot really lets you see that, in fact, they're far from normality. But hey, all's not lost if your data happens to be heteroscedastic or non-normal. In fact, in the next lecture, we'll talk some about simple transformations that you can do to satisfy your assumptions after all.